Hi, everyone. Welcome to Foresight's Intelligent Cooperation Group. I'm really excited to welcome our fellow from last year, Dmitrii Usynin, who's joining us from Munich, from the TU Munich. And he will today be discussing meaningfully evaluating large-scale machine learning under privacy constraints. You've given plenty of Foresight talks now at various different workshops, and it's always a joy to see just like how your research is progressing, and just I think it's becoming more relevant by the day. Please take it away. I'll share a lot more info about you in the chat, and I will also monitor for questions in the chat. Okay, that's it.
Thanks for the introduction. Let me find a way to share the slides. Okay, that works. Okay, fantastic. Hi, everyone. I'm Dima. I am currently a final year PhD student at TU Munich and Imperial College London. I am also working for a company called Oblivious as a research scientist, where we work on secure and safe decentralized AI and decentralized data sharing. Previously, I worked at Microsoft Research, was partner at OpenMind and Brave Research. So today we're going to talk about evaluation of large-scale machine learning models when there are privacy constraints. And these days, with the introduction of data protection regulations, these constraints are essentially everywhere. I'll explain and hopefully motivate your interest in how we can train better machine learning models when there are such constraints in place, how we can evaluate them in a meaningful way, and which methods we have as a community that we can leverage to do. If any of you have been to NeurIPS, I apologize because you would have seen at least 70% of this talk. So this is part of the proceedings that we had on trustworthy evaluation of machine learning models that we've given at NeurIPS last year. So some of the stuff is going to overlap. So the general principle behind machine learning in general, or any scientific problem that's driven by data, is that the more data we have, the better outcomes we're going to have as the community. That's because in this case, machine learning models get to see more features. They get to see subgroups they would not normally see otherwise, which allows them to generalize better, to adapt better to the tasks they weren't previously suitable for, et cetera, et cetera. And as I've already alluded to, it's very difficult to do it sometimes these days, specifically when we have a number of regulations such as HIPAA, California Consumer Protection Act, GDPR, etc. These prohibit us from sending sensitive data directly to the model owner to train them on their server, cloud, you name it. And they make it difficult as a result to establish scientific collaborations for settings which work on sensitive data. So electronic healthcare records, patient data, financial transaction history, etc. And there have previously been some attempts to solve this problem. So you may have heard of the two mainstream solutions, one being data anonymization, sometimes known as pseudo-anonymization, and the second one is known as decentralized training. So anonymization is exactly what it sounds like. There is no need for me to go over this. Decentralized training is a bit more interesting. So the typical paradigm of machine learning is that I ask you for the data, which you happily share with me. You send it to my server, to my cloud, it doesn't matter. And then I train the model. Instead of doing that, because then it requires you to share the data, I do it the other way around. So I send you the model, you train it locally, and you only ever share the results of the computation with me. This way, you essentially are staying in control of your data. This is something called data governance principle, and you decide yourself who is able to see it among the clients that have access to the results of your computation. However, there are problems with both of these approaches. Anything to do with anonymization, and the most mainstream one being k-anonymity, is that it's very difficult to actually assert that it works, because anonymization is an ad hoc series of methods which are applied to your database, to your data release, to some sort of information you're trying to share with the world. And you have to do it specific to a data set you're trying to release. As a result, at the time when you're releasing the data set, it may seem no one in the world knows what are you trying to anonymize. So all of your records have been protected really well. What you fail to account for is a notion of prior. So if the attacker has any public information available to them, linkable to your database, so we obviously share our dates of birth, our profile pictures, sometimes our marital status, etc., etc. A lot of this information can be linked to sensitive information releases, such as anonymized electronic healthcare records. And then the adversary is able to A, establish who you are, and B, extract your data with very high precision. There was a fantastic work in 2013, and bear in mind that's 12 years ago, which postulates that we only need 4 credit card transactions to uniquely identify an individual with a 93% certainty. only for transactions. As a result, we can't really rely on key anonymity when it comes to protecting sensitive data. All of the distributed learning paradigms are not helpful either, because as I mentioned before, it protects the governance of your data. Do you get to stay in control who sees the output of the computation? It doesn't actually mean that the result of the computation itself is private. And in addition to that, when I send you the model to train on your data, I actually can't assert that you've trained it in an honest way. You can insert various backdoors, you can, run many different poisoning attacks to get the model to train worse. And as a result, there are many different things that can go wrong in federated learning on its own. The good thing about it, though, is we can't really fix key anonymity because this is completely tied up in the notion of priors. So if we can't control the information that the attacker may get access to, we can't really fix it. But federated learning, swarm learning, peer-to-peer learning, and all the other decentralized learning paradigms are not about privacy. They're all about data governance. So we can actually add privacy at a later stage. And as a result, the process of training such models becomes more trustworthy in the process. There are many different ways to define the notion of trust, and I'm sure the list can go on. I just picked the top 3 from Google Scholar. In this work, we particularly concentrate on privacy as part of the definition of trust in this process. There are obviously other things like fairness, adversarial robustness, etc. But in this specific talk, we mostly discuss privacy. So to set the scene, where do we even begin talking about privacy? We need to establish which parties actually want to participate and what kind of privacy they're trying to protect. So the obvious one is the data owner. So this is you, this is the people who receive the model, train it locally, and then send it back. So you want to make sure that your data is safe and secure. The model owner, i.e. me, in this specific setting, I want to get out of this collaboration a useful generalizable model. So I need to make sure that when I send it to you, I'm not wasting resources. I'm not wasting money paying you for the data set that it's actually not good for me. And I'm trying to optimize my learning procedure to get the best model out there. And finally, there is also someone who very often gets forgotten. This is the end user. So once all of this collaboration takes place and once we get a trained model, we normally then send it to the end user who need the model to be representative of their use case. They need it to be generalizable, working for their specific data, and being trustworthy itself. So we need to make sure that the data is protected. From my perspective, the model is trained in an optimal way, and that the end user actually benefits from all of this collaboration taking place. And they all require different definitions of privacy and trust to be established when it comes to training such models. So to start with, the data owners, as I've already mentioned before, they need to make sure that the data that they give me as the model owner is safely handled. I, as the model owner, very often don't want to just give them the model weights. I very often want it to be proprietary because the weights are actually very expensive. Look at OpenAI, look at Anthropic. Their models are closed source. They wouldn't want to just send the model over to someone who controls the data, let them train it, and then potentially send something back. They would want it to be secure both ways. And finally, for the end user, the notion of trust is primarily concentrating on the model being robust, useful, and fair when it comes to dealing with potentially underrepresented end user populations. So when trust gets compromised, there are many things that can go wrong with any of these attributes. So this is a very famous example from Carlini's paper from last year. Essentially, what you can see here is you present a visual language model with an image of a stickman, and you ask, what is the person doing in the image? And as you can see on the right-hand side, the result is very interesting. And the reason this result gets generated is because the pattern applied to this image, you can see a lot of like really small gray dots. The pattern causes the model to misbehave. So all of the text that you're seeing on the right-hand side has previously been part of the training data set. And what you're essentially doing is you're prompting the model to somehow generate the response based on this text using this specific pattern. And you can generalize this pattern to any arbitrary task. So not necessarily just the model cursing. It could be model revealing training information, for instance. It actually gets worse. So the setting I described to you before, where I send you the model, you send me back the result of the computation in a federated learning, can actually get compromised unless you have any privacy preserving mechanisms appended on top of federated learning. On the left-hand side, so for both rows, you see the original training data, and then on the right-hand side is what I managed to reconstruct. And actually on the second screen on the right, you can see that the image labeled A is the original one, and everything else are different reconstructions based on the specific heuristics. The problem here is a lot of you may say, oh, this is just a generic image of a brain, it's a generic image of a lung, it's a classification task, these are easy, etc. If you look on the left-hand side more carefully, you would realize that the first two images are images of breast scans. On the first one, the left breast is missing altogether, which is not something you would want to reveal to the world. And on the one below, both of them are implants, which is, again, private sensitive information that you don't want to disclose. And as I've already said, there are many different arguments to be had here. This is an artificial setting. You reconstructed a scan. Does it really correspond to a person? And classification in general is an easier task to attack. We also managed to attack segmentation tasks. And the one on the top is a liver segmentation task, which again, it's a generic liver. It's really difficult to distinguish if it's a real person's liver or if it's just part of the training data set that doesn't really correspond to anything. But the one below is an image of a brain. And the problem with that is, if you pay attention to the images on the left-hand side, they actually have uniquely identifying tumors in the brain scans. And that is a huge privacy violation. So this is what can go wrong when you deploy federated learning without really thinking about it. Just because I can't see your data doesn't mean that the model doesn't memorize your data. So this is really bad. And if that wasn't enough, because obviously these are settings that I've constructed, this is part of my research, I was in control of the threat model, the attacks, the defenses, and everything. The final slide I want to show on this specific topic is, many of you may have probably seen this, is what happens when you actually apply this to models that have been deployed in the wild. So Millard Nasser has previously published work with his colleagues where they attack publicly facing models from Anthropic and OpenAI. And essentially, obviously, this has been fixed now, so you can go and try to do it, but the model is not going to respond in the same way. But they figured out that if you ask it to repeat something forever, it will eventually glitch out and start displaying the data that was part of the training data set. So the previous settings were essentially starting off from, this is funny that you can make the model do certain things like curse at you. This is problematic that you can reveal sensitive images, but this is just classification. Oh, this is a bit more problematic now because this is brain scans, which you can link to individuals. But it's a setting that you as researchers have controlled before. And now we're looking at a publicly facing model. And this was actually quite a big thing when the paper came out. You could go and try these things. And there were multiple other adversarial exploits that they used. And all of them happened to work across all settings. We can't really solve all of these issues at once with a single mechanism. Let's break it down into what we can do about it. There are two notions to privacy. There is the privacy of inputs, where if I don't get to see your data, that means it's private when it comes to inputs. So I shouldn't see the results of your computation in plain text, and the secrecy of your computation has to be maintained. If you think about encryption, secure multi-party computation, this is what protects the input privacy. So the adversary can't see what's happening. The privacy of outputs is very different. The adversary can still see what's happening and can feel the model, maybe even get access to the weights of the model, but it doesn't give them any advantage. So just because something is unseeable by the adversary doesn't mean it's necessarily private from the output's perspective, because as I've alluded to before, models are capable of memorizing things. And if your model has been trained using encryption, secure computation, it doesn't necessarily matter because it can still memorize a lot of sensitive information to the same capacity. And as a result, you need other different types of mechanisms to reduce how much memorization is happening in the model. So examples to fixing this is differential privacy, correctly implemented anonymization, and under very specific circumstances, synthetic data. I'll go to that discussion towards the end. So my area of research primarily focuses on output privacy, but I'll also talk about input privacy towards the end of the talk. So one of the methods that's most commonly used, and that's gained quite a lot of attention in the last few years, is differential privacy. So this is one of the formal, objective, meaningful ways to protect the output privacy of individuals. In a very simple terms, differential privacy is adding a little bit of noise to the results of your algorithm to make sure that you can't really distinguish who was part of the training data set. The example that I'm going to give you is actually really straightforward. Imagine that we have a data set. Everyone in this call is sharing some information about themselves. And then we have a second copy of the data set, which includes everyone except for me. If I run some sort of statistical algorithm calculating mean salary or mean age or any other statistical distribution, both of these data sets should essentially produce a very similar looking outcome. If that is the case, that means the result is differentially private because you can't tell which data set corresponds to having my data and which one corresponds to not having my data. This method, as you can tell from just sprinkle a little bit of noise, is essentially model and context agnostic. You can add Gaussian, Laplacian, many other exotic types of distributions to the output, and it will be differentially private. Moreover, you can actually bound and quantify how much information you're giving away to the world once you're releasing some sort of statistics. And the good thing about it, you can actually put a number on top of it. So you can go to your regulator or data protection officer and say, we are releasing this data, which is differentially private with a budget of XYZ. And you can then put this on your audit, and then it's very easy to track how much privacy you already spent versus how much privacy you still have remaining for you to release more information. It may look very scary when you look at this formula, but essentially the only thing to note here is that there are two sides of the equation. So there was the left-hand side, which is with my data. There was the right-hand side, which is without my data. And the amount of information which differs when I release both outputs to the public is bounded by e to the power of epsilon. And the epsilon is the number which corresponds to how much privacy it costs to release something. It's called the privacy budget. And there are many different other informal ways to refer to it. We're going to refer to it as a privacy budget. The important thing, and every time I give this talk, this is the same question which comes up at the end: what's a good budget? And the answer is, it depends. For machine learning, you would typically try to aim for something between 1 and 10. You train your model with methods for differentially private deep learning, and your final privacy budget should not exceed 10. 10, as you can tell from the equation, is already quite big. It's e to the power of 10. It's already pretty large how much information you're giving away to the world. But obviously, if you try to limit the information, you also try to limit the utility, et cetera, et cetera. A very quick example, just in case it still hasn't made complete sense. What we have here is a very simple data set of a bunch of statistics about a human being. So age, height, and weight. There are two different places where you can add the noise, and differential privacy is very flexible. You can add it to inputs, to outputs, to score functions, to your gradient descent training. There are many different places where you can add differential private training or differential private statistics release. The two really quick examples here is, let's add it to the noise. So you add your Laplacian noise to the inputs directly, and this is what corresponds to the top part of the image. Or you could add it to the aggregate statistics function. So this is your mean height, or mean weight, and mean age. And then you add a noise of a different magnitude. And the reason I want to distinguish between these two use cases is because one of the most complex things in differential privacy is actually knowing how much noise you need to add. Because the more we add, the more we perturb the output of the function, the less useful it becomes. And this is determined by something called the sensitivity. And if we take, not this specific example, but something more sensitive to variations of input, so let's say monthly salary. If we take my monthly salary, which I can only dream that it suddenly becomes £1 million, when I enter my data into the training data set, this £1 million per month hugely changes the amount of noise that needs to be added compared to the case when my salary could have been 2,000 or 5,000. As a result, you would need to add a lot more noise to go back to the point where with and without my data, outputs are looking roughly the same. And this is something determined by the sensitivity, which you can set in advance if you know your input distributions, or when it comes to machine learning, it's slightly a different question that we're going to look into in a second. Moreover, now that I've given you some insights into how differential privacy works, we want to make sure that we don't add too much noise, because the more you add, the more you perturb your output, the less useful the calculation actually becomes. And what we have been working on at Oblivious is trying to standardize what it means to be well protected when it comes to differential privacy, because there are many different companies which perform differential private releases. There are many different noise distributions, many different privacy settings. For instance, in the example that I've given you before, there were two users. Each of them corresponds to a single row in the database. Sometimes when we talk about financial transactions, a single user can have hundreds of thousands of transactions. So the unit of privacy is no longer a single row. It's more about a single individual who controls other rows. When we work with databases, and those of you working in SQL will see where the problem is coming from, we have all sorts of different joins and connections where the notion of privacy stems from an individual who controls that many rows in one database, which happens to be a foreign key in a different database, etc. I will share the links at the end of the talk, but we've created something called the Epsilon registry, so Epsilon for the privacy budget, where you can look into some of the common deployments that have been standardized by academia, industry, big tech, you name it. There are many governmental releases, there are many different private sector releases, there are a few academic releases as well. It's currently in the alpha version, so we will proceed to make it wider, to try to target more industries, to try to target different tiers of players, because sometimes just because a startup is operating differential privately doesn't mean much to other practitioners. But when companies like Microsoft or Apple or Google start putting into their products, that kind of sets the scene for everyone else to know what sort of budget they should be aiming for. So currently it's an alpha version. It's a lot of work in progress, but this year we're trying to essentially make it better, trying to expand it to more use cases. I've been talking a lot about adding noise. I've been talking a lot about knowing things in advance and appending things based on some sort of sensitivity. Now, those of you working with machine learning would very quickly realize, wait, but you don't know how much a single input point is going to influence your model in advance. If we take the simplest use case, which is a real function can go to infinity because it's just the way the function is designed, because it's that expressive, it can go as high as you want. And therefore, we don't know in advance when it's going to stop. So we don't know how much noise we need to apply. And this is where differentially private SGD comes in. So the idea is when we make an information release, we make something public. Here, it's a slightly different approach. So what happens in DPSGD is we don't make something public by default. We use the information contained in the data to make it public to the model. So the model learns in two phases, which is your forward propagation and your backward propagation. In forward, don't grill me if you're doing machine learning. I'm trying to simplify things down here, but essentially you're trying to propagate your inputs to see how right or how wrong your prediction is. And based on that information, when the model actually learns during backward propagation, this is when you update the parameters. So from the perspective of privacy, this is when the model learns from private data. And this is where the noise has to be applied to. This is a schematic diagram of how this happens. Essentially, if you imagine your typical machine learning workflow, when you do backward propagation, what happens is you compute the loss with respect to the model and with respect to the inputs that you fed into the model, and you try to see how incorrect your prediction was and how much you need to adjust individual weights and biases to account for that. This is what happens during backward propagation. You compute something called the gradient, and the gradient guides you towards updating your parameters to reduce this error in the next iteration. So the only difference between what I've just given you and the differentially private version of this is the notions of clipping and the noise addition. So what happens is, because we can't control the sensitivity because we don't know how much a single sample influences the model, we actually set bounds in it. So we set the clipping threshold. So your gradient norm could be at most X or Y or whatever variable you want to call it. Obviously, you can't know in advance what this number should be. But again, as a rule of thumb, anything between 1.0 and 2.0 works very well. Now that you've clipped, you know exactly how much noise you need to add. So then you aggregate your gradients together, and then you add the noise on top of them. So once again, just to reiterate, because we're operating in a privacy environment, in a private environment, each individual in a batch is considered to be private. So we need to look into each one of them and their individual samples, their individual gradients. Then we get to clip them because we don't know the sensitivity in advance. And then we sprinkle noise on top of that. This is how DPSGD works. And the only three key differing factors from a normal SGD is everything is per sample because each individual requires their own privacy. You clip things because you don't know sensitivity, and you add the noise. This is it. Everything else is identical, and it's very easy to integrate into existing machine learning workflows. However, because we're clipping, because we're adding noise, we're essentially adding geometric bias. We'll walk through why this is the case, but when you start using DPSGD, your underrepresented populations, potentially those who are already being harmed by being underrepresented, actually suffer even more. And as a result, there is a disparate impact of differentially private training on the populations that were initially harmed to begin with. This is a very simple schematic from 2019 from Eugene Bogdasaryan. Essentially, I don't have to explain to you much. This is what the image describes here. So if you have lighter skin, you're less affected by adding differentially private noise compared to people with darker skin. And the question arises, why is this the case? What exactly is there to make this effect much more profound in underrepresented populations? And now we come to the most theoretical part of this talk. What does the model actually learn under differential privacy? What actually happens under the hood? And differential privacy is designed to limit memorization of your sensitive data. It's true for any given randomized algorithm, data release, etc. Here we talk about machine learning. So everything is going to be with respect to machine learning. So when it limits memorization, the samples for which the memorization was actually required, they are the ones who suffer the most. The overall contributions for people for whom memorization was required is now bounded because they can only disclose X information due to differential privacy. And because the model can't memorize these patterns and because the information has been bounded, the model is forced to learn more general stuff, more generic information rather than specific to individuals. Is it really good for the end user? It depends on how you look at it. Obviously, this image suggests that it isn't, but I'll tell you why some of these things are desired in a second. So memorization is model's ability to perform well on the data it has previously seen. And this is what distinguishes it from generalization. So we want the model that generalizes well, because this is the model that works well on populations and data points that it's never seen before. But we also want it to memorize to some extent, because if you're part of the training data, you want the model to perform well in your data as well. Even though we often hear that we don't want memorization, it's undesired, in some cases, this is not true. Memorization is, in fact, not the opposite of generalization. It's something that happens on the side, and it's something that has to happen on the side. As long as generalization occurs, as long as the training data set contains samples of high value or of high memorization capacity, and as long as these samples and those memorized will be forgotten, we have to have memorization in the training of machine learning models. As I've already previously mentioned, differentially private training actually reduces the memorization capacity of the model. And this is particularly problematic for samples of high importance, or for those for which the loss of the model or the predictive error of the model is already quite high, typically those that are underrepresented. Very quickly, without going into details, we use something called the self-influence or the self-accuracy. We talk about classification settings. If a specific data sample has high self-influence or high self-accuracy, if you train, again, back to the two data sets, if we take the data set of everyone on this call and the data set of everyone except for me, we train two machine learning models and we try to make a prediction on my data, trying to predict, it doesn't really matter what we're trying to predict. You measure the outputs and you see how much of an effect the presence of my data had. If I possess very unique features, if my data is very difficult or very highly influential, you will see a huge difference, which tells you that the model doesn't memorize enough about me because my data is not in the training data set for it to be useful to me. And even though we have methods for formal, robust, and quantifiable privacy, specifically output privacy for machine learning models, sometimes these are not enough. Sometimes they actually contradict what the end user wants to achieve. So the methods such as differential privacy can provably bounce the information that gets learned from all samples, but specifically from the highly memorizable samples. And they reduce the risks of privacy violations. They're very often used by large companies, by many different countries. So the US Census actually used differential privacy 2 years ago. So it's something that does get picked up on by the regulators. But it also means that due to the addition of noise, due to clipping when it comes to machine learning specifically, we irreversibly lose information. And these underrepresented subgroups actually suffer a lot more than they should, because this is something which is desired by differentially private training. So even though we can train the model privately and we do have provable guarantees, everyone kind of suffers. So the end user and the model user actually get a model of worse utility, and the data owner who could have been paid for their data doesn't really get the same compensation because the value of their data with respect to the model is significantly reduced due to the fact that all of the very nice, very interesting memorizable points no longer get memorized. So that the model doesn't extract the same utility out of it. Now that I've spoken for quite a bit about the output privacy, we'll very quickly go through the input privacy. So this is your things like encryption, secure computation, etc., etc. I decided to go with one of the more widespread solutions to the problem, and this is something called trusted execution environments. You may know about it as Intel SGX or AWS Nitro. These are essentially secure enclaves where the computation happens hidden from the rest of the system. This is secure memory that's shielded from the rest of the CPU and the rest of the computer in very crude terms to make sure that the world outside doesn't see and doesn't tamper with what's happening within the secure enclave. It protects many different things, but the ones we're interested in for the purpose of this talk is confidentiality and integrity. This is schematically what it looks like. So your protected hardware resources are essentially not accessible directly by your untrusted users, your untrusted apps, and you get to stay in control of what code gets executed, what data goes in, and what's the result of the computation and what it looks like. You may already see that this doesn't have anything to do with output privacy because whatever goes in goes out in the same way. But now the adversary can't actually probe and change things. That's the notion of input privacy and how it's different to what previously discussed. The benefits are that you actually get input privacy for everything because whatever you throw in there, this is now private from the outside world's perspective because it's now you're controlling the secrecy of the computation. In addition to that, because these are hardware devices and they're designed by very well-established labs from Intel, AMD, etc., they inbuilt the guarantees of integrity as well as confidentiality. And this is the easiest thing you can do when it comes to setting up your input privacy, because all you have to do essentially is just buy yourself a machine which supports secure enclaves. This is a hardware solution. You don't have to change anything. It essentially works out of the box. And these days, so during Europe, we actually delivered a live demo. You can even place large language models in these enclaves. We went through a lot of hoops to get this to work from as a community from 2015 when they were just being adopted and you could barely fit a linear model in there to now 2024 and 2025 where we can fit Llama 3.2 into the secure enclaves to run them. And they're fairly computationally efficient. So while you do take a hit from homomorphic encryption or secure multi-party computation, these are much cheaper to use compared to the alternatives. Even though I did say that we can run Llama version 3, we can't really run anything larger than that. So year after year, they get increased capacity, they get much faster memory access, etc., etc. But we're still not at the point where we can fit any arbitrary model and any arbitrary information into the secure enclaves. And yeah, this is part of the demo that we gave. You can essentially put models such as Llama and run inference on them. So we're not quite at the point where you can train models there, but we are at the point where you can deploy them for inference. The second issue, which I can feel might be of big importance to the Foresight community specifically, is that we have to trust these devices. So companies like Intel, AMD, they all make these devices with all of these pre-built primitives for us to build secure apps and secure enclaves, but we have to trust the provider. We can't really verify a lot of stuff ourselves like we could in secure multi-party computation. This is something that we just have to deal with. This is a hardware device which may or may not be attackable through side channels. But you don't know this in advance because that's not something the manufacturer is obviously going to disclose to you. So we now come to the end of the presentation. I'm happy to share the slides and the links towards the end. Very quickly going through the links. So number one is the registry of privacy, of output privacy and differential privacy that we collaborate with Oblivious on. The second link is the tool you can use to train your own differentially private deep learning models, something called Opacus, developed by Meta. Fantastic framework. I've been following it since 2019, actually, before it was even called Opacus. And then you also have the guidelines for how to deploy differential privacy in the wild. by NIST, so it's very trustworthy. And finally, you have the docs on how to implement your own secure enclaves using online platforms from Oblivious called Anti-Granular. Essentially, this is as simple as running a Jupyter notebook where each cell is run in a secure enclave. So you get the input privacy. You can trial this for free. We have free tiers. We also host a lot of competitions. And this is something you can very easily integrate into your existing workflows. And I believe this is the end of the talk. Just about time, and I'm happy to answer any questions.
Amazing. Thank you so much. Really appreciate it. That was a pretty good primer, and then a lot more than a primer. Okay, wonderful. We have already one question from Micah, unless it's not relevant anymore. And this is also a reminder for everyone else. Feel free to, mic broke. Okay. Feel free to raise your hand with any questions, or if you can't do that, and if you can't unmute yourself, feel free to just drop your question in the chat and I will ask it for you to the best of my ability. Okay, we have Micah again. Let's see if it works.
I think it should be fixed now. Just a quick question. Which size of the Llama model were you able to fit into the TE?
I believe that was a 7 billion one. Yeah, I think it was 7 billion.
Okay, we have a question from Alan in the chat. Do you want to unmute and ask it, or shall I ask it?
No, it's fine.
Cool. Okay, cool.
I've been watching the secure enclaves for a while. In fact, I even programmed an early TPM, which was a royal pain. But there's a big financial incentive for, because that's where payments are done. And I would think that would violating privacy would not be a big incentive, and the manufacturers have a strong incentive not to be hacked on these things. Intel took a big hit with SGX. So I don't think that there's much risk in trusting these environments, given the incentives to attack them that have not paid off for the attackers yet. That's just a comment.
I would in general agree, but there is a reason I mentioned 2015 specifically. That's essentially how I learned about the TEs, because SGX wasn't secure. There was a timing side channel attack where if you have physical access to the machine, which is obviously like a really bad threat model to begin with, but if you have physical access to the machine, even though you can't see what's happening within the enclave, if you know the operations and the timing corresponding to each operation, you can reconstruct the weights of the neural network just by timing how long it takes to execute something. Yes, I fully agree with that. They have a very strong incentive because at the end of the day, they get completely screwed over by the regulators if something doesn't go according to the way they wanted it to go. At the same time, we can't completely not think about side channel attacks because it's something which is very difficult to account for. Timing attacks, operations, etc., etc. So
Yeah,
I agree with the comment.
Yeah, I agree. Apple Pay depends on its secure enclave. And if an attacker could get in there, they could make a lot of money, and simply haven't heard about that. So I think it's reasonable to have fair trust in the security of the enclaves. That was just my comment. SGX was the worst case I've heard of. For example, the original TPM that's on most PCs and laptops, I've not heard of a successful attack against those.
All right, we'll leave it at that. Feel free to get back to it also in the chat. Oh, Micah, you go.
Yeah, I just wanted some clarity. I think you already answered this question, but I want to make sure I got it. From you. You indicated. No, you indicated that for the outputs noising. Am I correct in understanding that is applied during backprop? That was the whole thing you were describing. Is when you say you're noising the output, what you actually mean is you're noising the backprop process.
Yeah, correct. You're applying most of the gradient itself, and yeah, super straightforward where it's like firstly clipping and then the noising.
Yeah. Okay. Thanks.
I have a question about the challenge that you submitted. And so generally for context, we usually ask our presenters to submit a challenge or like a problem that they would really like the field to solve. And I can read out the problem that you submitted, or you could maybe explain it in your own words. What do you prefer?
I think you can read it out and I can explain what I actually mean by it.
That sounds great. Okay, so the problem that Dima proposed is standardized, verified, and versatile open source frameworks to connect individual methods for trustworthy ML into unified pipelines. Currently, each research lab has their own benchmark libraries and custom connectors, making collaboration and verification of previous results significantly more challenging. So could you elaborate a little bit more, like what you mean here and how one could possibly make progress on this challenge?
So I've linked toward the end of the presentation something called atypical, which is a library which is really well used in the differential privacy community. But this isn't the only one. If you start putting things into Google like differential privacy without putting the words deep learning, you would get diffpriv-lib, you'll get Tumult Labs framework, you'll get OpenDP. And the problem is, unless you have the experience and the training that I'd had or someone else working on differential privacy had, you wouldn't know which one you should use, what's the scope, why is one better, why is one worse. But moreover, they're all written in such ways that it's not really easy for you to take the same machine learning pipeline or in general, any statistical release pipeline and just plug it in. In many cases, you have to go through a lot of hoops just to make that happen. Moreover, instead of trying to come up with something unified as a community. So I think OpenDP is fantastic for this. They're trying to bridge this gap as we speak, but we obviously don't know what's happening to their funding this year, given that they're based in Harvard. What they're trying to do is excellent. They're trying to build the open source community and initiative to tackle this challenge. But the problem is it doesn't necessarily fix the issue of trustworthy machine learning. There are other things like fairness. There are other things like robustness. There are other things like explainability. Whenever you try to target these problems one at a time, it's not very difficult. You'll find a framework that works for you. Whenever you're trying to make something fully trustworthy, so runnable and enclave with differential privacy, with explainable, you can't do that because a lot of these things try to access the same part. So the model, they try to modify it in the same place, and that is essentially incompatible. How do we solve this problem as the community of everyone? If you work in big tech, you just write a new library for yourself. You never publish it to the world. You use it internally, and you forget that this problem exists. But it doesn't fix issues for other research types, independent researchers, academic researchers, startups, small think tanks, etc. They don't have the resources to do it. And the challenge is essentially trying to come up, maybe forget about having the standardized framework when it comes to implementing it, but at least standardized theoretical framework of how things need to look like. Where do they connect to? What's your schema of inputs? What's your schema of outputs? How is it supposed to look like for the community from all of these different fields? Because don't forget, fairness and privacy are two distinct things. How can they all contribute towards something together and actually build a system which addresses all of these issues at the same time? You could also look, so OpenDP is fantastic for dealing with differential privacy issues, but you can also look at OpenFL. This is a standard for federated learning. And these are two huge, fantastic projects, but they're incompatible. The challenge is trying to make sure they're compatible and then the open explainability, I'm just making things up as I go now, or open fairness to also be integrated into the unified framework. Because we as researchers, especially the academic ones, are really struggling with getting access to this. I've seen how much better the internal versions at big tech look like. And I would like this to be available to the community.
Yeah, that's awesome. So if anyone's hearing this and feels inspired, that's a pretty good concrete path. And if you could lay out perhaps like a future, staying on the speculative lane here, in which like things are progressing as they should, there's more money pouring into development of the methods that you outlined here. Where do you think we could be in like 5 years? What's like a really strong goalpost, especially with the development of various new AI models from like DeepSeek to deep research to what have you that are just coming out almost on a daily basis, like in a positive world where the kind of like more privacy oriented research is keeping up, where could we be in 5 years?
I think we could actually be very far down the path in 5 years. I alluded to the version before Pecos. So Pecos used to be an internal tool in Meta, which was just an experimental framework for doing random things with DP. They actually had a branch in GitHub called Autograd Hacks because it wasn't something they thought would become a big framework. That was 2019. That's when it all started. Now we're in 2025. There are multiple such frameworks which are very well established. Pecos is one example. You have DP Transformers, which works on Hugging Face. There are essentially really big academic labs within these big tech companies, within Meta, within Microsoft, within Google, which are separately working on all of this. They managed to construct really impressive things for solving differential privacy issues. There are many companies which manage to do the same with respect to robustness and fairness. What we don't have right now is the unifying layer to link them together. I think this is very well manageable within 3 years or maybe even 2 years, given the incentives or given a company to work on this. Because right now, it's not the issue of tools, it's the issue of incentives. Because these companies are not incentivized to share and to integrate these things up until a new regulation comes in, which the AI Act within the EU is going to make things to do with robustness and fairness really difficult. This is when we're going to see emergence of open source tools for this. But up until the incentive is there, it's not the question of is it feasible? It is feasible. It's just people don't do it because they don't have the incentive to.
Yeah, and I guess there's always opportunity costs doing it that way. Okay, and what's next for you in particular? Like in the next year, could you give people an outline of your work? I guess either academically or like in various advising capacities that you have. What's on the horizon for you? And if people want to follow your work, where can they best find you?
I'm still going to be working on privacy one way or the other. So I am now merging between doing differential privacy for machine learning and doing differential privacy for more business-oriented use cases like databases, statistical data releases, etc., etc. So I am currently with Oblivious, and we're trying to solve both of the input and the output privacy at the same time. And that's where I'm planning to work for the time being. And you can very easily find me on Google Scholar because I still look for students to supervise, and we're currently working on synthetic data. Oh, actually, yeah, I promised to mention this and I didn't. Synthetic data is also not the means to privacy because it has to be generated in a secure way. Otherwise, you're still reading the same sensitive statistics within the data set. So working on differentially private synthetic data is something that I am currently concentrating on as well. But yeah, when you Google differential privacy, one way or the other, my name is going to come up, whether it's part of my PhD still, which I'm trying to submit, or part of working for Oblivious.
Interesting. Differential privacy for synthetic data. Yeah, I guess, of course, eventually it's like indirectly, you can probably infer a lot. Is there anything that I should have asked or we should have asked that we didn't, or any other items that you wish you had talked about that are now popping back into your mind?
I mean, it's a bit outside of the scope of this specific presentation. So I explained why memorization happens, why it's needed, why we would want to limit it and stuff. But actually, I haven't explained how we exploit it as attackers. That's an entirely standalone presentation on its own. It takes probably even longer. But if you're interested, just either message me or try to find me on Scholar, because that's my bread and butter. So I didn't start by proposing we need to make things private. I started with I broke the privacy of your protocol, and this is now the framework to fix it. So a lot of my work is actually a lot about exposing these findings and then fixing them afterwards. So that's an entirely different presentation, which we don't have the time, but feel free to message about it.
Cool. One last question from Alan is, does enforcing privacy hurt detecting poisoning?
Is a very complex question if I answer it in a long way. Yes, it does, because if you think about it, a lot of poisoning techniques, so just for explainability to everyone, poisoning is when you modify your data in such a way to hurt the training of the model. You can modify it at different times, but the most generic one is if the model is trained on my data, I change it, I add a few pixels like I've shown in the example, and it starts generating these predictions. And the reason that happens is because the poisoner, the attacker, is trying to target very sensitive points which are close to model's decision boundary. So is it really this I'm meant to predict, or is it the other thing I'm meant to predict? And because they're so close, the model is already confused as is. And these samples are normally more memorizable, more targetable, etc., etc. So yes, differential privacy affects this hugely because these are the same samples which are most influential, which are most memorizable. So if you reduce the memorization capacity of the model because you clip the specific samples, you also reduce their adversarial capabilities because you reduce the amounts they can contribute. Now, the reason this is good and bad, I'm sending you back to my Scholar. We've published a little bit on that. The reason it's good is very straightforward. You limit the impact. The reason it's bad is you send the model down the spiral of it needs to mostly concentrate on the typical representative sample. So you go from this distribution to this distribution. So now the attacker knows that you are only representing stuff in the middle. They have a better idea of how to generate samples, which are still within this middle majority distribution, which are now poisonable. And one of the works we published in 2022 essentially shows that if I'm trying to poison the data and the model is being privately trained, tough luck for me. I actually can't do anything because the impact of my poisoning goes down. But if this model then gets published, you can use it as a very strong baseline to generate new poison samples using this model as a baseline, the one that's been privatized. And if you generate these samples, they actually screw up any other model much better. So it's much harder for the attacker to try to target a specific setting, but it's much easier if something has been privately trained for them to use this as a generator for follow-up attacks. So that's a very long answer, but I can recommend the paper, which was Can Collaborative Learning Be Private, Robust, and Scalable? I think that's the name. There was even a GitHub attached if you're interested.
That was a pretty smooth description to a very complex question. All right, with that, thank you so much. That was a really great presentation, and I just shared a few follow-up links to you here in the chat so people can reach out to that. And if you want to reach out to Dima directly, I guess you can either try to find his email on the internet or you can just contact me and I will establish that bridge. Thank you. That was very interesting. Good luck. Also.
Thank you. Thanks a lot.